With pleasure.
You changed your topic?
I did. So I modified things a little bit. It's extremely close. So not that much is different.
If your preference is one certain thing.
Yes, we'll get some puns in. So this is a good topic for puns, by the way. So just throwing it out there. So it's a real pleasure to be speaking to you today. Excited about some work that my group has been excited about. This line of work on coming up with better ways to build machine learning models that can be aligned with human preferences, and what algorithmic questions are sort of hidden in these kinds of problems. So this is work with excellent students, Zach at Stanford, Hantao, who was undergrad Illinois at the time where we worked on this. So set up the problem. So this is a problem of inverse decision theory. It's motivated by a view that comes from psychology. So here the idea is we want to understand how human beings model other humans' decision-making. And the theory or hypothesis is that one way that we do this is that we ask, or we sort of collect a few examples of decision outcomes. And based on these few examples, we set up some inference of sort of how others might be making decisions. And so this becomes our model for other people's decision-making. In machine learning problems, there's a way to formalize this as a kind of human-machine interaction problem. Now I'll talk to that a little bit. So the idea is, suppose you're in a setting where the machine has some model that sort of, you can think about this as has some model of the probability of the label given inputs. Really what you need is something calibrated to ground truth. But for simplicity, suppose it actually has this conditional probability model. The machine knows this, but doesn't know the decision-making. So decision-making thought of here as a deterministic for an input, here as a label. And so the goal is that the machine will come up with an interaction process with a human that will help it infer the decision-making rule, given only a few examples. Generally, this is set up so that decision-making rule is optimal for some measure over this population, over this setting. The measure may be implicit or explicit. We imagine that sort of the human has some notion of optimal decision-making, potentially implicit in this setting, that's tied to the underlying conditional probabilities. And the machine doesn't know this, but all it can do is sort of get a few samples, based on these samples, try to infer a decision-making rule. And so this is the sort of challenging piece here is that you only get to see a few examples of these pairs. If you want to connect this to some other lines of work that are out there, you can think about this as actually very explicitly a special case of the idea of pre-training and then fine-tuning based on interaction. So it's sort of very much in that style of work. So popular in, say, language models. But this would be quite far from it. This would be a setting where we can give formal bounds on sort of sample complexity and things like that, query complexity. But it's the same style of problem of sort of, there exists some initial process that's maybe learned modeling distribution for the data, and now I want to convert this into a classification that's optimal for some metric that I may not know. And you can think about this as some decision-making rule. Okay, so you can show that this question of trying to find a decision-making rule tied to this conditional probability, if I think about it from a population decision-making point of view, this inverse decision theory problem can be reduced to a threshold search problem. So you might be familiar with this, for instance, in standard binary classification. You might know that if I know the population distribution, P of I given X, then the optimal for accuracy is thresholding at 1/2. And if there's a different metric, it turns out that sort of for most metrics, the optimal decision looks like some kind of thresholding, where thresholds might be at different places. And so this question of finding the decision-making rule under this framework can be reduced to finding the right threshold from the conditional probability model to the decision-making model. You might immediately have some concerns about gaps in sort of the framing. We'll come to this in a second, and some of the work that we do to try to narrow the gap from this model to what we think of as more realistic settings. The other thing to mention is that if you're thinking of one way to try to solve this problem is to think about this as a search problem, where you're trying to search for the right threshold. And every time you get a label for an example, this label gives you some information about where the threshold might be. So if the label is tied to a probability that's large and it's a 0, then it maybe suggests that the threshold is sort of kind of high. Conversely, if it's sort of small and it's a 1, then maybe the threshold is sort of really low in this setting. So the label that you get for a particular example tells you something about where the threshold might be. And as you get additional labels, you might imagine sort of a search process that moves the threshold around following the labels. So seen as a search problem, you can use a variety of search methods. One good approach, one that we'll use as sort of foundation of the work that we do, is a probabilistic bisection algorithm. So essentially bisection search that allows for uncertainty. So we have a slightly more general version of this problem, which we call a cooperative inverse decision theory. And the reason we set it up this way, there's sort of two ways to think about it. One is just existing gaps in the IDT framework that we try to fill, and I'll talk to those briefly. Another is thinking about this, and this way ties it to, we think, some useful framings and useful applications. So from the pure gap point of view, one way to think about this is existing IDT, as I framed it, is passive. It just collects examples and sort of tries to convert that into a decision. There's a bunch of uncertainty that can show up that the existing tool doesn't capture. So in particular, various kinds of noisiness, diversity of opinion, if you're doing this kind of inference over a population, missing or additional context that either is information that the model or the human has that's different, that might show up as noisiness. So some of our work is trying to fill in this gap. So we think about this as a game between a machine and a human. The machine we call an imitator. So the goal of the imitator is to try to infer, again, this decision rule. We'll start off with thresholding rules, and most of this discussion will focus on thresholding rules because, again, they're quite general and capture lots of different notions of what good decision making is. So sort of general enough to be practically useful. And the human is thought of as a demonstrator. So the human is showing the machine, again, examples and potential decision outcomes. And the goal, again, of the machine, the imitator, is to try to figure out the sort of the decision making that's closest to the humans. So you can try to solve this by, again, trying to learn a threshold decision rule. As mentioned earlier, both are trying to maximize some metric, again, directly coupled. So there's this effectively one-to-one. I'm being a bit informal, but I can sort of talk to details or send references offline of connections between metrics and thresholds. And the actual process that this will go through is that the imitator will pick an example to query. So this is the active bit, but doesn't know the performance metric that's sort of the goal is to optimize. And the human, the demonstrator, will respond however they like, hopefully matching their decision-making process such that then the decision-making function can be inferred. Okay, setup is clear. Yes.
So what is there a difference whether imitator pick an example to query or the human decides what to show? Like it's almost like a.
That's a good question. So the question is there a difference who's picking the example that's going to be queried? In this case, either the machine or the human. So we focus on, it's a good question, actually. The existing work thinks of the queries as random. The work we do thinks of the machine picking the queries under some sort of active learning style method. I think it's a very interesting question of what does this look like if the human is picking the queries under some notion of either ease or optimality or something like that. That's a great question, actually. I don't have an answer to that question. That's an interesting nugget to think about. Yeah. Any other questions? Yes.
Related to that would be, can the human modify the query slightly?
So the question is, can a human modify the query?
I won't answer the question you're asking.
Professor, pretty professor talking now.
Yeah. We allow, short answer, we don't have that in this setup. We allow for, and I'll talk a bit about sort of settings where they have different information. This is not the same as your question. It's not an explicit modification.
You're giving an example of
Yeah, Proof by.
Like I said, this is a good topic for fun, so have fun. Okay, any other questions? Okay, so I'll throw an algorithm up here. This is how you might do this with the PBA algorithm, this bisection search algorithm. So quickly walking through it, the way that you might, this is not that maybe helpful in very short order, but maybe by pictures. So one way that we can solve this and what you can do with probabilistic bisection search is you can start off with some prior over possible threshold locations, and you can do effectively like pseudo Bayesian updates is what we explicitly do. It's not fully for technical reasons, but close. And so you essentially sort of build likelihood over possible locations of the threshold based on the queries. And then the active bit is being able to figure out where to search. And we search at points of sort of, if you're looking for, say, the median potential threshold location, then we use that to define the threshold point to search. The way the algorithm actually works is that this threshold point, so this probability point, is converted into an example by sort of searching for the example that matches that threshold. And then the human gives a response to that query. That query response is then sort of gives directional information about whether the threshold is to the right or to the left of the queried point. This is used to update the Bayesian model effectively. And then over sequences, you can show that you'll converge to sort of a ball around the true threshold under this model. That's the setup. Okay, so fairly straightforward algorithm. It's worth pointing out some properties of both this problem and how it ties to some other existing work. So first, you can show that for this problem, the optimal joints policy is this bisection search approach, or at least bisection search is optimal. We find, and I'll talk about this a little bit more, that some of the key differences from at least classic active learning as applied to this problem are some of the notions of uncertainty that crop up in this setting. And so one of the ones that we identify is something we call the description experience gap. It's also been noted by other people, and I'll talk about this a little bit. Some initial simulations to try to understand it a bit better. And explicitly how it ties to uncertainty and preferences in decision-making. Okay, and as mentioned about the algorithm, so again, the idea is that we're going to update the potential location of the optimal threshold, and this boils down to tracking the measure of an epsilon ball around the optimal, and it's something you can analyze that sort of how quickly you are, what the probability mass is on this epsilon ball around the optimal, and you define a stopping time by the first time this measure exceeds a half, and this allows you to make sort of high confidence decision on where the threshold is. And the analysis, we can upper bound this process and use this to say something about convergence of this algorithm. A bit on the uncertainty, because I think that's some of the most interesting aspects of this work. So there are lots of sources of uncertainty. We have a subset that we analyze explicitly. So one is noise. So the human is potentially noisily optimal. There's some assumptions here, of course, that again, the human's decision process is well modeled by a thresholded. Either you can think about this as they're optimizing some metric under knowledge of the population distribution. This is one way to say it. Or you can think about it as sort of, said slightly better, they're well calibrated in how they're going from distributions of labels to decisions. So the calibration bit is what's important showing up there. Or you can think about this as some version of this model is a reasonable model for the human decision-making process. We'll show that at least some ways that this assumption breaks can be well modeled or captured by noise. And I'll talk through a noise model in a second. But again, you could imagine noise as being an issue with the framing so far. Another setting that the presented approach will handle well is decision-making when instead of inferring information from a single human, you want to infer over a group of individuals. And so the idea is you want some kind of consensus decision over a group. And again, if under some assumptions that I'll mention briefly, you can apply the same algorithm because this will look from the point of view of the algorithm as sort of noisy decision-making across noise across the individuals. Again, as long as all of them are making decisions, again, roughly calibrated to conditional probability of the label. And then we'll talk briefly about sort of systematic differences between the human and the machine, again, in cases where these can be captured well by this framework. So a bit on this systematic suboptimality. One way that we think about it is, maybe the simplest case in where this could happen, is when the features that the human and the machine are using are different. So for instance, it's actually commonly true that human decision-making, I guess, we often try to approximate using machine learning models based on features, but our features are all abstractions that don't fully cover sort of all the aspects of the decision-making process. And so there might be some gap between, even if all the assumptions are true, say humans are actually making decisions using this calibrated to some true conditional probability, there could still be a difference between the probability model that the human is using and the machine is using because they have different features. And so this will look like noise effectively because some of the features are missing from one or the other. And so this will look at additional uncertainty on the conditional probability model. Yeah, so in particular, in this case, the human will appear suboptimal with respect to from the machine's point of view. So we think about this as a description experience gap. This has been thought about some in the literature. There's a bit of work in the field thinking about this. It's one particular instance of this as a description experience gap. So it refers to differences between decisions made based on description versus based on experience. One way to think about this, cases where it comes up, is if you imagine querying a doctor for what decisions they might make in terms of, say, clinical decision-making diagnosis kinds of settings, the answer they give you if you describe a case need not be the same as the answer they give you if they're actually solving, like diagnosing a real case in a real setting. And so the sort of descriptive answer and the real world answer are different. One way to think about what might be different is the information content is a little bit different. Again, the description is some formalization with some small subset of features. The real world version is richer somehow. And again, there's this gap that's not captured in the set of features that's being measured. And so because of this, the human can behave quite differently in this kind of assistive game, given that the nature of the queries come as descriptions of examples. So look like features, essentially. So the effect that you might imagine of this is that the human will adjust this decision rule because, again, it has a different underlying model. And some of what we can show in details in the paper is that this will lead to sort of changing the nature of the decision threshold, either sharper or less sharp. And I'll actually skip ahead a little bit. So one way to think about this is that instead of thinking of the decision rule as a straightforward threshold, which is maybe this example and what you might, what we've set up as the model for this setting. So again, we have an underlying conditional probability. We have a threshold as sort of decision-making process. One way to describe this, or one model that we found meaningful for capturing this gap and many other kinds of noisy decision-making settings, is thinking about this as, again, still a thresholded decision, but now the threshold is randomized. So now it's, instead of having a single threshold, you have a distribution over thresholds. And we can show that this model is sufficient, for instance, to capture the setting where the sets of features differ between two decision makers, and they're interacting in order to make a decision. So if you like, the gap in probability modeling can be captured by just a distribution over possible thresholds, which is what is shown here. And so this is the sharpness idea that I was trying to capture. A little bit more formally, we have an approach that works generally what we call, or the range of settings that we try to capture well are settings where the decision-making process is cumulative. So this is thought of as a bit richer than the pure thresholding decision-making process. The cumulative, we mean that the expected value of the decision is a monotone function of the threshold. So it's sort of a weaker condition than pure threshold. It can itself be a random variable. And roughly the key takeaway and a property that we'll exploit is that if the decision-making process is cumulative in the way that we're describing here, then we can model it as decision-making with a randomized threshold. So that's the main takeaway of this slide. Okay, so as mentioned, this is a non-realizability issue. Again, this gap between what the model has and what the human decision-making is. And this gap can be well modeled in many settings by, again, this randomized threshold. Okay, so the actual algorithm can change a little bit to capture more noisy settings. So for instance, here's an implementation of the algorithm that allows for noisiness. So the main change here is that instead of the PBA algorithm that takes sort of a single vote and uses this to make a decision, the information about where the threshold should be is now set up as a test. So we have a voting process here that sort of, you can think of a bunch of different ways. You can think about it as just testing whether H is equal to 1 or 0 because it's now random. Or you can think about it as, I guess, directly as voting. But the main thing that we need and the main thing that we employ for both the algorithm and the analysis is that now there's some confidence level that gets tied to obtained signals. This confidence level is obtained by either setting this up again as a test or voting sufficiently. So you sort of query sufficiently often. So to talk through some examples, you have a group, then you'll sample the group enough times to have confidence alpha in the decision for the group, the median decision for the group. If you have an individual with a noisy process, again, you might query multiple times because, again, this looks like randomness in the decision. Okay, so we have some results. I'm going to just talk through the sort of high-level one. If we have time, I might cover some of the other details. But anyways, one of the results here is that if you have the class of models that we've outlined, so this class of models that, again, well captured by randomized thresholds, which you think of as richer than existing work and then rich enough to capture lots of interesting phenomena. And as long as the confidence is sufficiently high, so greater than half, then using this pseudo-Bayesian update in the way that I just described using the algorithm allows you to show convergence of this algorithm. So convergence of the threshold to the optimal threshold. Optimal threshold. So the analysis is close to existing analyses of the PBA algorithm. We have a modification that uses a random walk argument that, again, I'll invite you to look in a paper for more details on. And the main takeaway is that if the noise is not too bad, the algorithm sort of doesn't suffer all that much, if you like. That's the main, one way to think about the main takeaway. A little bit on the analysis, again, quite high level, but again, we're trying to capture this epsilon ball around the optimal and sort of how it updates over the sequence of the algorithm. You could show that you can model it well as a geometric random walk. And then we just need to understand the stopping time to understand convergence of this algorithm. So that's the main tool that we use. Okay, a little bit on experiments. So we do a few simulation experiments to try to understand how this method works in sort of pseudo-realistic settings. So the first one I'm showing here is comparing the CIDT method to IDT. The main difference is, again, the existing approach uses passive algorithmically. One of the main differences is that the existing approach uses passive samples, whereas CIDT actively queries for the next sample. The other big difference is, again, noise tolerance compared to the previous approaches. Here we're comparing log error of the threshold compared to the optimal, showing that effectively you think about this as an active learning kind of plot. So it's showing that using active querying increases accuracy much quicker than doing this passively. We also looked at different kinds of noise and how this might affect decision rule recovery. So pseudo simulated setting. First, we have on the left a noisy setting. So the noisy setting here is simple constant noise. The decision is flipped with the probability 0.5 to capture some uncertainty in the decision maker's process. So it's simple constant noise. And what I'm showing is both the underlying decision likelihood. So probability decision equals 1 for this problem. And comparing it to quantiles of the estimated threshold. So I skipped a little bit in the past. I should briefly outline here. So the way the algorithm works, we get to pick what quantity we want to estimate about the distribution of thresholds. In all the algorithmic examples I put up, we use the half to estimate the median effectively. But you can choose any quantile you like. This allows you to estimate the whole distribution as opposed to just single point of the thresholds. You can estimate the whole distribution of thresholds in the case where it has a noisy threshold. That's the main takeaway here. Okay, so we do this to show that, again, this works for choosing, like if I'm interested in either modeling the whole distribution or I'm interested in potentially different points for threshold decision making, I can capture this in different kinds of noise. On the left, it's a constant noise, label flip. On the right is randomized decision threshold, so a setting where, again, the decision matches the expectation is monotonic with respect to conditional probability, but then it's sort of randomized after that. So modeling this idea that we have a pool of decision makers and we're sampling from them. Okay, we also have examples capturing this idea that there might be different subset of features for the decision maker and the algorithm. So again, a sort of simulation approximating this description experience gap. And we show that, well, one, there's some effect. This looks like noise. This ends up lengthening, instead of probability of decision being this sharp threshold thing, it now looks like a much lengthened, because there's now a distribution over possible decisions. But we're able to capture it reasonably well in this setting. We have some real data experiments. So yes. Okay. Oh, okay. So real data experiments, not real people, but real data. Standard data set. This is important, as you might imagine. Okay, that's fine. I'll finish quickly and have time for questions. So we model this to, again, capture this idea of different kinds of information. So we include different feature subsets for the decision maker versus the algorithm. and measure the absolute value difference between, let's say, the threshold and then the optimal threshold, assuming that the optimal decision or what we're optimizing for is accuracy. So optimal threshold for a half. And we show what happens with different versions of the algorithm compared to the existing approach, which is the CIDT, both passive and then doesn't capture or handle noise appropriately. Okay, so to summarize, the main contribution here is cooperative inverse decision theory approach, which is meant or designed to be a framework for helping to capture human preferences in machine decisions. In this particular setting where we're interested in the gap between probability models of the world and then actual decision-making processes, particularly when they're noisy. We've analyzed an approach, this sort of randomized search approach with sort of testing in the loop, showing that it does pretty well. We have some analysis in the paper, so I'll invite you to take a look for some details. And we've shown that you can capture a lot of the nuances of different kinds of noise processes that we think might be meaningful for this kind of problem. So far, we've mostly focused on binary decision-making. So everything here has been sort of predicting binary label. So we're extending this work to think about more complex decision-making problems beyond binary predictions. And we've done a few user experiments, but there's a lot of space. It's always the fun part of this kind of work is all the real human-facing stuff. So a lot more on that part of the work. Okay, I'll stop here if there are questions.
We have time for questions.
I guess this fits a little bit in your going beyond binary, but I was thinking, why not think about the discrepancy between the features, the descriptions, and the actual experiments as a sort of a decision that you have to make on what features you're sharing, some sort of a constraint, and I can, because right now you assume that you're asking for a sample, but maybe you're asking for a sample in a smaller feature.
I see. So make this explicit. You can. So one good reason to do something like this. So the comment is just for Mike that you can imagine settings where your design process explicitly selects over both examples and subsets of features.
Yeah, like when we ask, usually we ask certain features, and that's what we are asking. And
this makes
you're
sense.
right that would be a discrepancy between understanding your decision making on the more. And this kind of goes back to, of course, my obsession with this zooming in and getting high resolution as you get more.
I think our plug is you should read a paper.
Yeah.
And your plug should be. You should
No. This is very interesting.
Yeah. I think it's a good idea. I guess out of the box, if one did this, you expect the method to still do reasonable things.
Exactly.
I'm curious if one can. So this isn't telling a strategy for how to subselect the features to ask questions on, which I think might be interesting.
But I think like as you ask more questions,
yes,
there is this ability to zoom in on more sophisticated questions, which the model should capture in some sense, and it will be pretty.
Yeah, I find this intriguing. So sort of allow for noisier at the beginning and narrow down as you get closer.
And that's how we learn most of the time anyway.
I think that's a very reasonable idea. We haven't played with this, but it makes a lot of sense.
That was my related question. How do you set up the Bayes and learning part? But so like.
Sure. So the algorithm?
Yeah. So the update rule, right? I mean, doesn't it depend on how quickly or fast or how many samples you need to learn?
So
always my question around Bayes.
The convergence will depend on quality of samples. And we have, I guess, what I showed is just sort of asymptotic results. We have some finite samples stuff there too in paper. Does that answer your?
Yeah, more or less.
Okay.
Yes, Maxim.
There's really cool stuff. Many years ago, there was this paper titled very provocatively "Human Automatic Complexity" by Jerry Zhu collaborators. And they were trying to basically see, can humans actually do humans in fact reject decision rules that just fit noise and instead zero in on informed decision rules? And I mean, I don't know what happened to that work. They presented it in Europe, and I think they discussed some implications for cognitive science, judgment, decision making. But it seemed like there could be some connection.
I vaguely remember the paper because I do remember that. It was provocative at the time. I didn't think about it when we were working on this. I think it's a good idea to take a look.
Because I mean, what you're talking about more like active decision making, which then could be connected to Sasha Rockman's work on sequential automatic complexity. See, if you write a paper called humans again,
Title, the paper writes itself.
basically, yeah. It's like an award-winning paper. Right?
Okay.
Thank you so much. Take a break and we'll be back.
Could be something. That was recently. Interesting.